Hi, this is Module 2, Lesson 2, Please Be Discrete. So we talked about discrete and continuous last time. Before we start into this one, we're going to be talking about domains. So when we talk about domains, what you need to know is what type of numbers will go into what we put in for x values for our inputs. So this chart gives you an idea of what some of those options are. So you have real numbers. Numbers are really split up into real and imaginary. As far as we're concerned, we're just going to deal with real. Real numbers are any number. Pretty much any number you can think of, that's a real number. Probably at this point. You probably don't know imaginary numbers. Real numbers can be split into irrational and rational. So irrational would be numbers like pi or square root of 4, fifth root of 8. Those are all irrational. Rational numbers can be put into a fraction form. So 4 could be turned into 4 over 1. 0.3 repeating would be turned into 1/3. So any number that can be turned into a fraction is rational. Rational can be broken up into integers. Specific rational numbers that are whole numbers, positive or negative, are considered integers. And then integers can be broken down into natural numbers. Natural numbers would be like your counting numbers, 1, 2, 3, 4, 5. So when you're looking at domains, you're looking at these different types of numbers. Now, typically, scroll down a little, you will only use real numbers because either you're going to be able to use any number or it's going to be more specific. So most of the time it's going to be a real number, an integer, so a whole number, positive or negative, or a natural number. And we're going to use the notations of R, Z, and N when we go to write those. So we will be doing those as we're doing this first lesson here. So let's start with our first problem. The Library of Congress in Washington, D.C. is considered, oops, sorry, I'm going to undo that line off there. Zoom in a little. Okay, the Library of Congress in Washington, D.C. is considered the largest library in the world. They often receive boxes of books to be added to their collection. Since books can be quite heavy, they aren't shipped in big boxes. If on average, each box contains about 8 books, how many books are received by the library in 6 boxes, 10 boxes, or in? So now we want to find an equation. We need a table, a graph, and an equation to model this. So just like last lesson, we need all 3 of these. We need them again. And then we're going to identify the domain. So let's start with our table. So the table, I'm going to put over here. We want boxes, and we want books. So one box has 8 books. If we get a second box, we're going to have 16 books. Third box will have 24, and so on. So knowing this pattern, what am I doing? Oh, plus 8. Plus 8. So my equation, f of n equals my starting value, 8, plus what am I repeating continually? Adding 8, and I'm going to do n minus 1 because my first term is an 8, so I started with my first term. Now, if you notice we have 2 8s in here, we can actually simplify this into just f of n equals, what am I doing with 1 to get 8? What am I doing with 2 to get 16? What am I doing with 3 to get 24? I'm just multiplying 8 by them. So either one of these equations would work for our function. So I'm going to jump over to our graph. So this is, let me get a pen going here. This one is number 1. So we had our graph of boxes and books. 1, 8, 2, 16, 3, 24, 4, 32. So they're all positive numbers. So I only need the first quadrant. This is my boxes. This is my books. Again, on down here, I'm going to go every other. 1, 2, 3, 4, 5. And then if I do books, notice I'm going from 8 to 32. So I might want to count by 2s. I might want to count by 4s. Let's go. I'm going to count by, if I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Barely get 4 up here. So let's go by 4s. So 4, 8, 16, 24, 32, and 40, 48. Okay, so go to make my graph. 1 is 8. 2 is 16. You notice my slope. I'm basically going up 2 over 2, up 2 over 2. And I can actually just keep going if I want. Now the question is, do I connect them or not? Well, it's books. I can't have half a book show up. I can't have half a box show up. So it is discrete, which means I'm going to leave my dots alone. All right, so now I got to go back 6 boxes. I'm going to go over here, and if I put in a 6 for n, I have 8 times 6 would be 48. If I put a 10 in, 8 times 10 would be 80. So that's how many books to answer their questions. Now we're going to do domain. So I'm actually going to, undo. I'm actually going to scroll down and do my domain. Undo. I thought I hit the button. Select. Okay. Scroll down, and I'm going to do my domain down here. So domain, this will be 1b. So how we write this is domain is, first I want to identify my variable. So I'm going to use n as my variable. Then we kind of do a line, and we'll say n is. What kind of numbers can we put in for n? Well, we determined it was discrete. And if we look at our table, it was all whole numbers. And they were all positive. So the type of number that is positive whole numbers is natural numbers. That's one way to write it. A notation way to write it is same beginning. N, this kind of a funky E looking thing. N is, here's where that notation comes, natural numbers. So you basically write that letter N reads N is natural numbers. Same thing up here. This is words. This is symbols. Let's move on to number 2. Many of the books at the Library of Congress are electronic. If about 13 ebooks can be downloaded into the computer each hour, how many ebooks can be added to the library in 3 hours, 5 hours, in hours, assuming the computer memory is not limited? So, table, graph, equation. Table. We need hours. Hours. And we need books. So the first hour, we can do 13. The second hour, we can do another 13, which puts us at 26. The third hour, we can do another 13, puts us at 39. So I know I'm starting with 13, and it looks like I'm adding 13 each time. And I started with my first term, so I need an n minus 1. Notice I have my double 13s. Let's simplify this a bit. Start working towards more efficiency if this makes sense to you. What am I doing to 1 to get 13? What am I doing to 2 to get 26? Well, 13 times 1 is 13. 13 times 2 is 26. 13 times 3 is 39. Either one of these works. It's an or. All right, let's go graph this. So this one is number 2. We've got hours and we've got books. First hour is 13. Second is 26. Third is 39. Fourth is 52. Again, we're positive numbers. So I'm going to go this way. I'm going to put books. And I'm going to put, oh, nope, backwards. How do I undo? I did that backwards, didn't I? This one is hours. This one is books. So 1, 2, 3, 4, 5. And then I know I'm counting by 30s. I want to get to 50. So I'm actually just going to go by 5s. So 5, 10, 15, 20, 25. Ooh, I'm not going to really have room, am I? 35. Nope, we're going to have to undo that. Let's erase these guys here. We'll keep my lines and just undo that. Let's go by tens, so our dots in between are the 5s. 10, 20, 30, 40, 50, 60. There we go. And it's okay if you realize partway through, oops, wrong ones. Try again. So 1 is 13. That's going to be not quite to the 15 mark. 2 is 26, because I'm going to be a hair above the 25 mark. 3 is 39, just below 40. 4 is 52, just above that. 5 would actually be 65. Okay, so can these be connected or not? Well, could I have a partial book? Yeah, you could download half of a book. You could also check at 30 minutes and see how many have gone. So this one would actually be continuous. So I'd want to connect the dots. So now coming back here and working on domain. Let's scroll down and do a domain for this one. So domain, I'm going to do it down here. 2b. Okay, so my domain. What numbers could I have put in for x? Well, we said we could do 1 hour, we could do half an hour, we could do 3/4 of an hour. So that means we could do real numbers. But can I have a negative half? -3. No. So we're going to say n is positive real numbers. How this looks in notation form, n is real numbers, and then we do a little semicolon here. N is greater than equal to 0. Here's how I show the positive. Here's how I show its real numbers. So again, you read this as n is my variable. N can be real numbers, but n has to be greater than or equal to 0, meaning it's positive. All right, let's go down to page, oh, didn't know I could move those. All right, let's go down to page 2. The librarians want to work to keep the library orderly and put books back in their proper places after they have been used. If a librarian can sort and shelve 3 books in a minute, how many books, we have 3 books in a minute, how many books does the librarian take care of in 3 hours, 5 hours, or in hours? Now notice here it says minutes, here it says hours. So our labels are different. So we need to make sure that we take that into account when we're making our tables and graphs. So first of all, let's make our table. We have hours and we have books. And this is shelving books, so we have whole books, not digital. So in the first hour, how many books can she shelve? Well, if you can do 3 books every minute, and there are 60 minutes in an hour, that would be 180 books in 1 hour. So, going back over here, 1 hour would be 180 books. 2 hours would then be 360. 3 hours would be 540. 4 hours would be 720. And notice we're kind of already answering these questions because it says 3 hours. Nope. It says 3 hours. Here's 3 hours. If we do one more, let's go ahead and do one more. 5, 720 plus 180 is 900. We've now answered this question. 5 is 900. We did that on the last one too. It was 3 and 5. And I think by the graph, we had answered the 5 as well. So just make sure you're at least hitting the numbers they ask you to hit. All right. Table, graph, equation. Let's do our equation while we're right here. So f of n. I'm going to jump to my more efficient equation. Each time, what am I doing to 1 to get 180? 2 to get 360. 3 to get 540. I'm just taking 180 times my number. Because if I go back one, wouldn't it be 0 and 0? 0 plus 180 times n, same thing. So there's my equation. Let's jump over and do our graph. So this one is number 3. So let's make our table again. Hours, books. 1 hour is 180. 2 is 360. 3 is 540. 4 is 720. And we said 5 was 900. Again, we're all positive numbers. It's kind of nice when we just stick with one quadrant. Here we've got hours. Here we've got books. 1, 2, 3, 4, 5, 6, 7, 8. And going up the side, I've got to get up to 900. So I'm thinking I'm going to go up by hundreds. 100, 200, 300, 400. Here's 500, 600, 700, 800. Oh, 900's all the way up here. So 1 hour is 180. Let's see. Oh, close to 200, not quite. 2 is 360, so that's a little bit above the 350 mark. 3 is 540, just below the 550 mark. 4 is 720. 6, this one's 7. Trying to see on here about halfway through. And then 5 was clear up here at 900. 8, yep, 9 right here. And since I'm shelving books, I actually want it to be discrete. But also notice that in between here, I'm actually going to have a bunch of little dots where the minutes are, right? Because if it's 3 books every minute, I'm technically going to have a dot every 3 minutes. So even though it's not a full straight line, connected line, there are definitely small dots in between in here. I'm trying to keep on that line, but make them all separate. So just keep in mind that even though it's discrete, there are more points than what we're putting in here. Okay, back to our questions. No domain in this case. They didn't ask for a domain, so let's just answer question 4. Would it make sense in any of these situations for there to be a time when 32.5 books have been shipped, downloaded into the computer or placed on a shelf? So Can you ship half a book? Can you place half a book on a shelf? No. So the only one, only the download makes sense. Okay, number 5. Which of these situations in 1 through 3, so the ones we just did, represent a discrete function and which represent a continuous function? Justify your answer. Well, we said number 1 and number 3 were discrete because we could only get or shelve whole books. Number 2 is continuous because we can download a partial book. All right, so we analyzed our results a little bit there. Let's keep going. Number 6. Okay, a giant piece of paper is cut into 3 equal pieces. Then each of those is cut into 3 equal pieces, and so forth. How many papers will there be after 10 cuts, 20 cuts, n cuts? Table graph equation. Noticing a pattern with these. Let's make our table. So we have cuts and we have pieces. So with 0 cuts, so it gives us here 0 cuts, I have 1 piece of paper. With 1 cut, as you can see, I have 1, 2, 3 pieces of paper. With 2 cuts, so here's 1 cut, 2 cuts, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Or sorry, this is 1 cut. This would be the second cut. So I have 9 pieces. 3 cuts, I take all of these into 3 equal pieces, meaning 27 cuts. So now let's go back to our original, since 0 is not 0, 0 is 1. What I'm starting with is 1. And what am I doing at each time? Well, this is a times 3, times 3, times. So I need times 3. And since I'm repeating multiplication, it is an exponent, n minus 1, because my, do I need an n minus 1? No, I don't. Oh, what's going on with this? Why is my stuff moving? I'm not sure what's going on here. There we go. That's weird. See if I can undo some of this. Doesn't like what I'm doing. Okay, we'll just erase this and rewrite it. Okay, sorry about moving that. Okay, so 1 times 3 to just the n, because if I plug in 3 to the first is 3, I get an answer of 3. Or you could just put f of n equals 3n, because anything times 1 is itself. Okay, let's look at the, let's go jump over and do our graph. So this one is number 6. Number 6, we had cuts and pieces. 0 cuts, 1 piece, 1 cut, 3 pieces, 2 cuts, 9, 3, 27, and 4, 81. Yep. All right, again, whole numbers, positive. So this is cuts. This is pieces. 1, 2, 3, 4, 5, 7, 8. And I have to get up to 81. So I think I'm going to go by tens. 10, 20, 30, 40, 50, 60, 70, here's 80. So just label enough that I know what I'm doing here. So 1 is 0. Or sorry, that's not right. Undo. I read that backwards. 0 is 1, way down here, at the bottom. 1 is 3, so I'm still less than 5. It's still pretty tight down there. 2 is 9, getting a little higher. 3 jumps up to 27. 4 jumps up to 81. Oh, right over here. I can line everything up. Here we go. So now if I'm doing my cuts, do I want to connect these spots or not? Well, can you have half a cut? No. Can you have half of a piece? I mean, either you have a piece or you don't, so it would be discrete. So knowing it's discrete, let's talk domains. So domain, my variable's in. In is, we know it's positive numbers. We know it's whole numbers. And we can summarize that up as natural numbers. We can also write it in notation form. Note, you don't have to do both of these, but you need to be able to recognize it for when you get your reflections. So in is natural numbers. All right, let's answer our question C. Would it make sense to look for the number of pieces of paper at 5.2 cuts? Nope. We said it's either a cut or it's not. Can't have partial cuts. Would it make sense to look for the number of cuts it takes to make 53.6 papers? Why or why not? No. Can't have really partial pieces, can you? Pieces. Either you have a piece or you don't. I just realized we did not go back up and answer our 10 and 20 question. So let's jump in here and fill that in. So put it in our equation. If f equals 10, I want to do 3 to the 10th. And that is a nice big number of 59,049. And then if we do f of 20, 3 to the 20 is a much bigger number. It is 401. That's a 6. So that way we didn't forget to answer all those questions. So we got our ends, we got our answers to this. All right, let's jump to 7. We're getting there. Okay, so 7 says medicine taken by a patient breaks down in the patient's bloodstream and dissipates out of the patient's system. Suppose a dose of 60 milligrams of anti-parasite medicine is given to a dog, and the medicine breaks down such that 20% of the medicine becomes ineffective every hour. How much of the 60 milligrams dose is still active? So we want to know what's left in the dog's bloodstream after 3 hours. 4.25 and in. Table graph equation. Okay. So notice the question is how much is still in there, but our percentage is how much has left. So if I start with 100% and 20% has left, That leaves me 80% still active. So anytime you have these percents, take a look at it and say, am I using that 20% with the 100? Or do I need to take it out and see what's left? So think about what the question is asking before you start just plugging in 0.2 or whatever into your equation table. So we have hours and we have, we'll just say medicine. So at the first hour, we have, or sorry, 0, we start with 60 milligrams of medicine at the very beginning. After the first hour, 20% has left, which means 80% is still there. The second hour, we have another 80% left. The third hour, we have another 80%, so 30.78. Really, you should only have to go to tenths. And because it's asking for 4.25, we've already done the 3. Look, here's 3 hours, 3 hours. 4.5, let's just go ahead and put 4.25, not 4.5, 4.25 in here. Actually, I take that back. Let's do 4 first, just so we've got, just a minute, there we go. Let's just do a 4 so that we keep this part consistent. 4, 24.58, 24.58. Now I'll do the 4.25. I'm going to just put it in my chart, but we haven't figured out how we're making this yet. So we said this was going to be 80% each time, right? Times 0.8 times 0.8. So if I go to make my equation, f of n equals my starting amount, 60. What am I doing over and over? Multiplying by 0.8 repeatedly, which means it is a exponent. So this is my equation. Now to be able to figure out the 4.25, f of 4.25 equals 60 times 0.8 to the 4, can't read that, to 5 power, which when you type that in equals 23.24. So there's our 4.25. 23.24. Okay, let's go graph this. So this is number 7. So we have hours, and technically our label is milligrams. So I'm going to put milligrams in here. 0 is 60. 1 was 48. 2, 38.4. And for my graphing purposes, I'm just going to do the nearest tenth. 30.7. 4 was 24.6. Again, all positive numbers. Just do this like this. So this one is hours. This one is milligrams. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do every other here. Let's decide what I want to count by. So if I have to get up to 60 and going down, let's do 1, 2, 3, 4, 5, 6, 7, 8. I have 8 lines. That's about, now we can do 10, I guess. Let's just go by tens. 10, 20, 30, 40, 50, and that puts our 60. Oh, don't need a 1 there. Our 60 right here. So 0 is 60, right on there. 1 is 48, so it's just below the 50. 2 is 38 point something, so that's a little bit below the 40. 3 is 30.7, so that's just about right on that 30 mark. And 4 is 24. Oh, did I do that one too low? I did. Let me erase this one. 3 and 30. Here we go. It's right there. 24 would be about right here. And so you can see there's a little bit of a curve going on here. It's not as obvious since it's kind of crammed up together a little bit. Then if we did 5, we'd have a little bit better there. But could I check medicine in between the hours? And would there be a different amount as we go through? Yes. Yes, there would. So you can see we're starting to get kind of a curve going up here. It's not consistent as we're going down. So it is continuous. So let's do our domain now. So domain is, well, I can use decimals. It's continuous, which means I need all numbers in between. But I also need positive. We're not going into negatives. Can you have negative medicine in your body? No. So positive real numbers. Where's my eraser? Real numbers, which also can be written in is real numbers, and then n is greater than or equal to 0. Sorry, that's so sloppy. There we go. So that's the notation as well as the other. All right, let's answer these questions here. Would it make sense to look for the amount of active medication after 3.8 hours? Yes. You could check partial hours. Because it is continuous. Partial hours. Would it make sense to look for when there is 35 milligrams of medicine? Yes. Because we can have partial hours. And thinking in terms of like logically, do you want to know when there's 35 in there? Well, that's almost half the medicine. So they would like to know, like if it's pain medication, at what point, maybe at 20 milligrams, it doesn't work anymore. It's really ineffective. So if you get to the 35, maybe you're trying to see, well, is it close to how ineffective is it at 35 milligrams? At a certain percentage, maybe it's not worth it. So yes, those would be okay because you can have the partials in there. All right, let's wrap it up with some analogies. Analyzing what we're doing here. So which of the functions in model 6 and 7 are discrete and which are continuous? So 6 was the cuts, 7 was the dog medicine. Number 6 was discrete because cuts can't be in half. Number 7 was continuous because the medicine was gradually leaving. Run out of room. Leaving the dog. Okay. To a different color so don't get confused. 9. What needs to be considered when looking at a situation or context and deciding if it's best with discrete or continuous? Well, the domain. If the domain can be partials, then it can be continuous. the domain needs to be certain numbers, then it's discrete. So your domain is really a big clue on this one. All right. Next one, number 10. Describe the differences in each representation, table, graph, and equation for discrete and continuous. Okay, so for this one, if we look at a table, I'm going to do these in different colors so they're not mixing up since I don't have a ton of room. Table. It's hard to tell, but whole number domains are a clue. I'll say can be a clue for discrete. Okay, for graph, dots mean discrete. Lines mean continuous. I apologize for the sloppy writing. It's very hard to do this on a screen. Okay, and equations. So for an equation, recursive. So if somebody gives you a recursive, I don't think I spelled that right. Try that again. Recursive. If someone gives you an recursive equation, you know it is discrete. Means it's discrete. And I'm going to actually go ahead and keep going on here. Explicit is continuous. So if somebody gives you an explicit equation, you assume it's continuous, but it can be used to represent both. So if someone gives you a recursive, you can only put in whole numbers or their starting number and then jump whatever it says. So it has to be discrete. But explicit, if they give you an explicit, you technically can put any number in there, which means it's continuous. But notice how all of ours, whether they were discrete or continuous, we put an explicit equation in there so that we could find bigger numbers, 10, 20, 30. So we write them to represent both explicit. But if someone gives you one and said, is this discrete or continuous, the explicit would then mean continuous. Last but not least, number 11, I'm just going to make a little line and put it down here. We got a little space to go here. Which of the functions modeled in this task are linear? Which are exponential? Okay, so linear. If you look back to all of them we talked about, the ones that involved the book shelving, so numbers 1, 2, and 3 were linear because they all added to get the next number. 1 added 8 each time for every box. 2 added 13 for every downloaded book. 3 added 6. What was 3 was, 3 books every minute. So it was 180 every hour. So it added 3 books a minute, 180 hour. Continuous. Oh, sorry, we're not on that one. It's exponential. Exponential was number 6 and 7 because they multiplied to get the next number. So in 6 was the cuts. It was a times 3 every time. And in 7, it was a times 0.8 every time because it was going down. But they were exponential because we involved multiplication. So thank you for joining. And that is it for lesson 2.